In this lecture, we're going to talk about reactions that involve what's called a halonium ion. So let me first just get that out in front of everybody. So the halonium ion looks like this. It's a three-membered ring where we have an X kind of bridging or connected to two carbons simultaneously. That X has then a net formal positive charge. That X is either bromine, chlorine, iodine, not really fluorine. So these are group 7 or 17, whatever. And so what I do is I do a quick formal charge calculation on these, and I see group 7 element minus, and we'll consider these, we'll still have two lone pairs of electrons to achieve an octet. So we have 2 bonds, and we have 4 non-bonding or unshared electrons. That gives us a +1 charge. Okay, so this is the halonium ion. And so halonium ions are going to be important for the next two reactions that we talk about. These halonium ions are formed when we take an alkene and react the alkene with X2, where X2 could be molecular bromine, Br2, Cl2, or I2. Okay, so these spontaneously form. Now, what I want to do is I want to kind of just get that in front of us as we prepare ourselves for these mechanisms. So what's going to happen is I'm going to show you the first mechanism, which is the dihalogenation of alkenes. The dihalogenation of alkenes is where we take an alkene and we add to it X2, and we get out R with X's on either side. Okay, so how does this reaction proceed? Let's consider a mechanism that I'm going to kind of establish as more correct. Strong words. What we know. How about that? What we can say. What we can say. All right, stuff's complicated. And sometimes we have these beautiful models, and I could draw curly arrows, but I may draw too many. So let's just get this out here. What I'm saying is that right away, the alkene is going to engage the X2, which I'm showing as XX, and it's going to give rise to a halonium ion. There's my halonium ion. And we're going to have X. In addition, we'll have X minus. Now, if you look at this, it looks like the charges cancel each other out on either side. We have net neutral on the left, net neutral on the right. And so everything is set up properly. So far, so good. Now, what do we have here? Well, we've got an R group attached to one side of a three-membered ring, where the three-membered ring contains a non-carbon atom with a positive charge. This is just like a protonated epoxide. And I'm going to show that protonated epoxide with an elongated carbon-oxygen bond at the more substituted position to show that we have preferential nucleophilic activity at the more substituted position. And so this is equivalent to me saying, you know what, I'm going to, instead of drawing this as more of an equilateral triangle, I'm going to have an elongated carbon halogen bond in my halonium ion. It's the same structure to show that the nucleophile will want to add to the more substituted position because this longer bond is weaker. This behaves the exact same as a protonated epoxide, just that now we have X minus coming in, and X minus is going to serve as the nucleophile to do the ring opening reaction. And that's going to convert our halonium ion into a dihalide, which is the product. So how do I approach understanding this mechanism? Well, I first want to appreciate that an event that happens when I treat an alkene with a dihalide is I'll form a bromonium ion. Okay, so when I form the bromonium ion, then I do chemistry similar to a protonated epoxide, where we're going to ring open the three-membered ring by some nucleophile adding at the more substituted position, which is what I have shown. Okay, I could draw some curly arrows for formation of the halonium, but it's not always super correct. Okay, let's just show it. So some curly arrows. This is just to kind of appease your curiosity, which I know everybody is loaded with curiosity at the second to last lecture of a module. But anyway, some curly arrows. Some sarcasm there, sorry. Some curly arrows for formation of the halonium ion. How do I think about this? Okay, first of all, what we want to get in front of us is that the alkene can be depicted as a resonance structure where we put the positive charge at the less substituted position, the negative charge at the more substituted position. This allows us to see how things could interact. Now, namely, we're going to interact with the dihalide. I'll put brackets around this just so I can capture those are resonance structures and not different structures. It further emphasizes what the resonance arrow is trying to show. Okay, now that's going to interact with X attached to X. Let's point out that X is a good leaving group, right? It's a halogen atom, so bromine, great leaving group. We've talked about that before. So we could have the negative charge come and attack what happens to be another halogen atom, but it's attracted to a good leaving group. So it's attacking the halogen because the halogen's attached to a good leaving group that can leave. Now, I have no problem with that first step. I have problem with this step. This step implies that we're going to form a carbocation intermediate, and that's not real. Rather, before we can form anything like a carbocation intermediate, the lone pair of electrons sort of come back around and bite down on the positive charge, allowing us to form our three-membered halonium ion. And so I say this isn't super real. If you need to draw this to get you your halonium ion, I'm fine with it. But I just want us to recognize that this isn't what happens. Instead, the alkene sort of engages the X, and then simultaneously, the alkene adds electrons and the halogen back adds electrons, so that we simultaneously form both sigma bonds in concert as the bromine is sort of positioned fairly equally between the two carbon atoms. Of course, it's elongated in cases where there's not symmetry, which I've shown by having that elongated bond. So again, if you just want to jump right to the halonium ion, I don't blame you, because that's what happens. We don't form the intermediates, and the intermediates are the most important part of the mechanism that we consider. Okay, so let's look at some examples of this. It turns out that this, that if we have, let's just go ahead and draw like alkene plus I2, and we want to predict the products. So what we're going to do is break the carbon-oxygen double bond and put iodines on either side of the carbon atoms that were once double bonded to each other. But if you want to consider a mechanism, we could first draw the halonium ion pair where we have plus, plus, minus. Now I'm going to have the iodine come in and do underneath attack, splitting open the ring, and that's actually going to give rise to this depiction after ring opening. But due to free rotation, these two structures are the same. So we do the underneath attack just like we would with the protonated epoxide, putting the iodines on opposite sides. It doesn't matter in this case, but it can matter in some cases. So what if we consider a structure like cyclohexene? So if we consider a structure like cyclohexene reacting with Br2, what will the product be? Well, it turns out that the product of this reaction is the trans alkene. That is the alkene where one is a wedge and one is a dash. And you could have either orientation. They're just enantiomers of each other. Both enantiomers would form. I could even put down here enantiomers. That is, when I say plus enantiomer, that's with a dash on top and a wedge on the bottom. Okay, so what's the mechanism for this? Well, here we're going to have formation of the bromonium ion, a halonium ion where bromine is in the center. Now, what you'll notice is that I'm going to have a cis three-membered ring, and that's because three-membered rings can't form in a trans orientation. Like if you're going to build a triangle, you can't have like one be a wedge and the other one be a dash. They wouldn't connect. So we have a cis three-membered ring. Now what's going to happen is the negative charge on that three-membered ring is going to attack underneath. And we have a symmetric molecule, so it doesn't matter which side. We're going to split this open. It's important to note, though, that this goes underneath or opposite of the side that the ring's on. I could have the ring being both dash or both wedge, just as long as they're both the same. And then the thing that comes in and attacks, the Br minus, is going to attack from the opposite face. And in this case, I get the enantiomer, which is the bromine that just attacked becomes a dash. The original bromine is a wedge. So I could have gotten the enantiomer, the originally drawn structure, by attacking the bottom carbon. I could have attacked there instead because it's a symmetric molecule. It shouldn't show preference. Or I could have had the bromine with two dashes instead of two wedges. The important thing is that this is trans when possible, and it seems to be mostly possible in the case of rings. So when we saw hydrogenation of the rings with H2, we saw a syn addition where the hydrogens are on the same face. Here, our nucleophile is adding to the opposite face that the halogen that was originally part of the halonium ion was added. So we have our halonium ion, and it's being it's reacting with an alkene by underneath attack to give a trans product. Now, what I want to do is move on to another reaction that involves a halonium ion, and that's the Halohydrin reaction. In the Halohydrin reaction, what we do is we actually replace the X minus nucleophile with water. This is similar to the hydration reaction that we had talked about previously, where we had H plus and X minus adding together to the alkene. Here we're having X for the halonium ion, kind of X plus, and then H2O adding instead of the X minus. So what does that look like? What we're going to do is we're going to take our same alkene and we're going to add some X2, and we're going to add a bunch of water. Now, how do we add a bunch of water? We're going to let our water be the solvent. And the solvent allows us to see that this is going to be added in excess. The outcome of this reaction when we have substitution is we're going to have X be at the less substituted position, and then OH be at the more substituted position. Okay, now how does this work mechanistically? Well, mechanistically, or the mechanism for this reaction, is that we'll first let our alkene react with X2 to form our halonium ion pair. Now, there is an X minus that's present, but that X minus is in low concentration compared to a bunch of water. So let's just remind ourselves that this is in excess. So when the electrophilic halonium ion that spontaneously forms when we treat our alkene with X2, that electrophilic halonium that's ready to accept a lone pair of electrons will now accept electrons from the water that's used in excess. Now, where is it going to go? It's going to attack the more substituted position and it's going to do so underneath the ring. So underneath / trans. Okay. So we let the water attack. The water is going to carry with it two hydrogen atoms, which, like the hydration reaction, is going to give us another intermediate. So we're going to attack that position and put the X over to the right side on the unsubstituted side. And then H2O is going to be on the underneath side now with a positive charge on oxygen because both of the hydrogens came along for the ride. The R group is now up here. Cis or trans don't matter in this example, but we'll look in a ring example in a second, and we'll see that, yes, cis or trans does matter in that case. Okay, so the hydrogen is actually going to be lost to give rise to a neutral alcohol with an OH. And so we do see a buildup of H+. H+ does not promote this reaction. It's not a catalyst for a reaction, so it does build up, and we have to take that into account when we clean up the reaction. But the important thing is that we add a halogen, which is our halo, and water, which is our hydrin. The Halohydrin reaction. Okay, let's look at an example of this with a ring now. So we can actually look at some real chemicals, not X2 or R groups. Okay. Let's pick this for example. So in this case, what we're going to do is we're going to see this react with Br2 plus excess water. Keep emphasizing that this doesn't work if there's like an equal amount, because water is not a good nucleophile. But if you increase the concentration, it will outcompete the addition by Br minus. Okay. So the first thing that we have to recognize mechanistically about this is we're going to form a halonium ion. I don't need to draw curly arrows for that because the curly arrows are not often ultra correct. Now we could form the cis halonium ion, cis at the bromine, and this is our bromonium ion, plus its enantiomer. And I could consider just one or the other, which one I feel like going with. And so the methyl group that was part of the carbon-carbon double bond is still attached, and it forms now a stereocenter. And so we could draw that as either a wedge or a dash. Both are enantiomers. If you notice, we flipped all the wedges and dashes. We have enantiomers. What do you need to know? Well, just use one. Both enantiomers are formed, but with two stereocenters in the final product, 2 to the second power is 4. We have 4 possible stereoisomers. These two, the two enantiomers resulting from reaction of these two products, along with their corresponding 2 diastereomers. The 2 diastereomers are not going to be formed, as we'll see. Okay, so what we're going to do now is add H2O. And my goodness, I'm sorry, I've forgotten the charge. We're going to add H2O. Now we have 2 spots to attack, both of which are going to be underneath or opposite that of the ring. We could add to the side with the methyl group, the carbon with the methyl group or the carbon without. The carbon with the methyl group is more substituted, so we'll add there. And then push the electrons onto the bromine atom. We're going to do so with underneath attack. And again, we just pick one to go ahead with. Let's say we pick the left. So from the left, what I'll notice is that my bromine was once part of a wedged ring, so I'm just going to leave it there. And again, both enantiomers are formed. The one with the dash would also form. So this is going with underneath attack, and that's going to actually position the methyl group to be up, and the water came in opposite that of the ring. So the methyl group is pushed up, the water came in opposite or underneath the forming ring to give us an intermediate where the oxygen has 2 hydrogens. We just need to lose one of those, and we have our OH and our Br. These two are trans to each other, but it's not a trans geometry because there's a third group. So trans, like overall trans, doesn't apply, but the important thing is the OH and the Br are trans to each other. Okay, so a complicated reaction to be sure, but it actually builds on all the principles we've talked about in this module. Three-membered rings with positively charged non-carbon atoms stretch and strain so that we can accept a nucleophile at the most substituted position. Here, the nucleophile is water. It's just an oxygen with two hydrogens. We have to lose one at the end of the day. The underneath attack is going to position that as being opposite to that non-carbon atom. This is the exact same mechanism as when we had a protonated epoxide in the presence of water or alcohol. So hopefully you're able to make those connections. Let me know if you're not, and we can help you. The mechanistic unity is kind of what we're looking for. So the next video will kind of wrap up with the last few reactions to look at for this module.